Hello everyone, thank you all for joining my presentation section. I am Zhouyu from University of California, Riverside Arcs Lab. In this presentation, we will demonstrate a state-of-art of a collision-inclusive trajectory planning algorithm, which works in unknown environments. As robots increasingly venture outside the protected lab environment and into the real world with uncertainty, guaranteeing collision avoidance becomes an even more challenging task. If a conservative local planner is employed to avoid collisions in cluttered environments, the robot may not be able to find a feasible path to the goal, even if one exists. At the same time, recent advances in material science and mechanical design have helped introduce robots that can safely withstand collisions. For example, small-legged robots with exoskeletons, aerial robots with protective cages, and soft robots. Conventional planning and navigation strategies have used geometric representations of boundaries to define collision-free paths with convergence guarantees. Three main categories of planning algorithms exist for planning in partially known environments with local information for local collision path. Those strategies are planning directly by reacting to sensor data, map-based planning using sensors to build maps first, and then planning based on those maps, and planning to maximize exploration coverage. For more realistic planning cases, we need to consider trade-offs and balancing between performance and risk exist in the actuation of the planned path. One of the methods to eliminate the risk is utilizing the concept of inevitable collision states for safe path planning. However, identifying appropriate ICS can be challenging for robots with noisy actuation and sensing. It may cause the robot to generate a conservative path, which weakening the performance of the robot. Different approach is to generate an explicit risk function based only on partial information of the robot state. While current risk-aware approaches can describe trade-offs between risk and reward of collision avoidance in mobile robot navigation, they cannot help to determine how to best utilize those potential collisions. In recent works, models for reflection on obstacles have been developed to capture velocity, position, and uncertainties that result to collisions. That includes Galvin model and stochastic model describing the reflection and boundary following behaviors. These works can be leveraged to explicitly include boundary interactions within robot planning algorithms. When the environment is known, collisions can serve as a practical means to improve the effectiveness of the trajectories. Through dispersion of energy and redirection of momentum, colliding agents can thus be endowed with greater maneuverability. A mixed integer programming-based method can be used to generate collision-inclusive trajectories. In this paper, we design a reactive sampling-based planner for collision-resilient robot navigating in unknown obstacle-cluttered environments. Consider a global map populated with an unknown number of static obstacles. Our goal is to select a fast trajectory considering the collision with boundaries. The state-of-art of this work is divided into 5 parts: sampling on the frontier, pruning the candidate states, select the state on the frontier based on our optimization function, generating Waypoint and B-spline, A switching maneuver is designed since our algorithm encourages the robot utilizing potential collisions, and thus the robot may face collisions when following the pre-planned trajectory. In the following 4 slides, we will describe each part of the algorithm in detail. In the figure of this slide, we first notice that the local map contains 4 parts. Note that U contains all partially observed obstacles with the exception of their observable boundaries. We can see that we generate a set of candidate states on the frontier. While we utilize frontiers, our method is different in that we do not set bounds on the velocities based on inevitable collision states, but instead, we evaluate and predict the effect of potential collisions in unknown environments. We do not have to make the robot stop at the frontier. Our method can also be tuned to switch between collision exploitation and safety. The sampling configuration space C is represented as S times theta times V, where S is the position space, theta is the velocity direction space, and V is the velocity value space. We select possible both position and velocity in the sampling process. In the figure, we can see that the candidate states lying on B2 are pruned because they are closer to the candidate states lying on B3. The candidate position on B3 are closer to the goal, and they are separated by free space F. The position-based pruning does not remove candidate states that may be far from the goal, like the candidate states on B1. Instead, it removes states that are expected to have the same effect if selected towards exploration. After the position-based pruning, velocity-based pruning selects the states leading towards an unobservable space which encourage exploration. To determine an intermediate state QS, we follow this objective function. The goal is to find the shortest path which balancing the risk and benefit of colliding with the environment. This is where the novelty of our cost function arises. Instead of designing a stop maneuver to ensure the robot always stays in free known space, the cost will generate a potential to make the robot go and exploit the unknown area, colliding with the boundary and using collisions as the tool to steer towards the goal. After we get the states, we generate appropriate waypoint to get the B-spline. In this way, we generate the trajectory as a previous collision avoidance algorithm. However, in our algorithm, we encourage robots utilizing potential collisions. To handle the potential collisions, we integrate a mechanism of switching maneuvers. If no collision happens, the robot simply moves through. If a collision happens, there are 2 possible cases. First, colliding and following the boundary until appropriate disengage. It is shown in panel B at the bottom row of figures. Second, a flow-through strategy which essentially recomputes the desired trajectory for the robot after collision, as it is shown in panel C at the bottom row of figures. We can see that the blue line is the desired trajectory before the collision, and after the collision happens, the desired trajectory changes into the yellow line, and the robot's actual moving trajectory will be something between those. It is shown in red line. After that, we implement our proposed algorithm on the collision-resilient OmniPack platform which we build in-house. The body of the OmniPack robot is surrounded by a reflection ring that enables it to collide safely with the environment and rebounds from it. The OmniPack robot operates in a 2.4 by 2.4 confined corridor environment with rectangular pillars serving as static convex obstacles. This video shows a trial for high-risk path with intentional collisions. We can see that the robot do not deaccelerate on the frontier and try to utilize collisions. This video shows a trial for high-risk path without intentional collisions. You can see some obvious deaccelerations when the robot approaching the frontier. This video shows a trial for low-risk path. It chooses longer path with wider corridor. It also keeps a slow velocity compared to the previous strategies to make sure the robot stops at the frontier. In this experiment, we performed 20 trials for each of the 3 strategies. We can see that high risk with intentional collision path makes the robot choose to go through narrow gaps and collide with the edges without the acceleration. High risk path without intentional collision makes the robot choose to go through narrow gaps, but it deaccelerates to go through those gaps and try to avoid collisions, though it is not always possible. Low-risk path makes the robot choose to go through wider passes in the map and deaccelerate to make sure that it goes through those passes without collision. Experiments reveal that integrating collision harnessing in online planning can decrease both the arrival time and the path length of the generating trajectories when compared to high-risk trajectories without utilizing collisions and risk-aware safe trajectories that avoid collisions altogether. As mapping time increases, both mean arrival time and mean total path length of all 3 strategies increase, but our proposed approach continues to yield better results. In summary, we present the state of art of a new reactive planning algorithm suitable for collision-resilient robots in unknown environments. The planner allows for potential collisions to be harnessed to improve robot navigation in obstacle-cluttered environments. We contribute foundational tools to support the cases where robots might deliberately choose to collide with the environment. Future work will focus on analyzing in detail the effect of the various quantities that determine the degree of pruning. We also focus on experimental evaluation in more complex environments. That's all for my presentation today. Thank you for joining my presentation.